Hi, my name is Cody Doucette. I'm here with Yao Chao, Guanshen Zhang, Shigang Zhu, and we are the Maple and ODL team for our cloud computing class in spring 2015. The mentor for our project is Andreas Volmy. The broad goal of our project is it's very SDN and OpenFlow based. Just to give you a broad overview of what SDN is it stands for Software Defined Networking. And it's a mechanism that separates the control and data planes. So instead of in the traditional approach where you have the control plane distributed between many nodes in the network, you can pull the control plane out of the network into a centralized controller, which then makes control decisions for the rest of the nodes in the network. And the way that it communicates between the switches and the controller is via some standard protocol, which is usually the OpenFlow protocol, but it's not necessarily the case. So this programming model has enabled a lot. It's enabled flow tables to be the standard data plane abstraction in networks. And it's also brought about a protocol for this switch and controller interaction. And all of that is great, but we're still missing a key piece to realize the full benefits of this abstraction, which is a programming language and some greater programming abstractions to make this better for users. The current practice for SDN programmers is to be very explicit about how they're going to specify flow patterns. So they usually have to do it in a declarative way, meaning they have to specify what they want the flow patterns to be, but not necessarily how they want them to be in place. They usually have to worry about low-level details, such as managing the different patterns in the flow rules. They have to worry about priorities and things like timeouts. And the programming languages that they use can be kind of restrictive. They often have to use specialized programming languages to do this. On top of that, there's other problems, such as needing to maintain consistency as the network changes, for example, as ports come up and down, or as links come up and down, and as policies change. There's different OpenFlow standards. They have to worry about switch hardware diversity. And they also have to worry about scalability and distribution concerns, or how the flow rules get distributed throughout the network. All of this can make for a very frustrating experience for the programmer. So instead, we can take another approach using an algorithmic model. And what the algorithmic model is basically just where the programmer defines a function f, which is a high-level function. And it's high-level because all it needs to know is the packet and some kind of environment. And it's going to take in those parameters and output a route. So this is going to describe how the packet should be forwarded, but it does not describe how the flow tables are configured. So now we're describing more of the how and not so much describing the what. The goal is to make this high-level function f be defined using a general-purpose programming language. So you could envision using Java or Python, or maybe even a functional language like Haskell. And then the controller is going to conceptually run f on every packet entering the network. So here's an example of a simple policy f that just contains a map to map MAC addresses to locations. And so this function f, on receiving a packet p, is going to take the source Ethernet address from the packet and add that to the map so that it knows what port to send packets from that source from. And it's going to check if the TCP destination is 22, then return a null route. So this is a kind of security measure or access control that can be put in place. Otherwise, it's just going to retrieve from the map the location that it should send the packet based on the Ethernet destination. And then it can compute some path. Maybe it'll compute the shortest path in this instance, and then return that path. So it's doing a few different things here. It's updating its environment by updating that map data structure. It's reading packet data, and it's also computing and returning some path. All of these pieces are important because we need to be able to observe what the function does when it sees a packet in order to generate flow tables. So what the Maple programming abstraction can do is it's going to observe the dependency of f on packet data. And for every observation that it makes, or every series of observations, it's going to compute a trace. And a trace is basically a series of assertions or observations about what kind of read happens. And then the leaf of each trace is an action, so something like drop, or it specifies a path. Once those traces are in place, they can be combined to build a trace tree, which is a partial decision tree for that function f. So at any given time, we may not have reached all execution branches of f, but whatever packets we've seen can be used to build this partial decision tree. The benefit of having the tree is that once we have that, we can easily generate flow tables from the trace tree. So this model is very flexible, and it'll enable some good programming abstractions, but it can introduce performance bottlenecks if it's naively implemented. And that's because the controller is probably not going to have the computational capacity to invoke f on every single packet. And on top of that, there's also bandwidth issues and latency issues. So in summary, Maple is an SDN programming system that enables this algorithmic model by addressing these performance challenges. It allows for simple and intuitive programming while achieving high performance and scalability at the same time. So that was the brief introduction of our project. Now we're going to talk about the tasks that we actually accomplished, the tools that we used to do it, the documentation that we used, and then finally at the end we'll do a demonstration of our project. Our project consisted of 3 different tasks at a high level. Our first was to implement a basic Maple programming abstraction, not necessarily all of the bells and whistles that it contains, but at least a naive implementation. We also aimed to implement a Maple adapter in Open Daylight, so to leverage the code that Open Daylight already has to enable Maple. And finally, to also provide some sample algorithmic policies, which we're going to demonstrate later as well. So on the right-hand side of this slide, you can see that we've kind of shrunk the area that the user needs to be concerned about when trying to program flows. So they just need to specify the algorithmic policy. And then Maple is basically the controller that's going to compile the flow rules and pass them to some message layer, something like Open Daylight or Floodlight, which will then distribute those rules throughout the network using OpenFlow. In terms of the project to make a Maple adapter in Open Daylight, we first had to become familiar with the rather large source code repository, and we also had to become familiar with the tools that they use, such as Maven, which we used as a build environment. The first thing that we did was to add Maple as a bundle to the existing code base, so to make it interact with the code. And after that, we slowly added functionality for receiving and sending packets to switches, receiving port up and down and also link up and down notifications, so we had to add listeners for that information. And we also had to implement functionality for installing and deleting flow rules on switches. And these things weren't necessarily easily exposed to programmers in Open Daylight. So in some cases, it took us a while to do the right digging to find what we needed to do. But once we were able to get this functionality, then we could give it to the Maple part of our code, which could then do further processing and call upon this code as well when it needed to do things like send out packets or install flow rules. So it kind of defined a bidirectional interface. In order to do much of this work, we had to take advantage of the module-driven service abstraction layer in Open Daylight. And this is basically the layer that contains all of the low-level functionality that we need to leverage, such as the actual message passing abstractions and installing flow rules, things like that. So we had to tap into this MDSAL in order to get Maple to run. On the other side of our code, in the Maple code, we first defined boilerplate code for various types of packets and flows, such as classes to define matching for flow rules and actions for flow rules, different types of packets like ARP packets, Ethernet packets, etc. All of that was needed before we could do any kind of Maple rule generation. The first step of the actual Maple algorithm was then to observe how algorithmic policies examine packets to build traces. So this is observing things like when the high-level function f reads a field from the packet. Once we have that, we could use those traces to build trace trees, and then write functionality to actually compile those trace trees to flow rules. And as the network changes, or as the policies in the network change, we needed to augment the trace trees and update the flow rules as necessary. So as an overview, we have two different repositories. We have an ODL Maple repository, which contains the adapter, and we have a Maple Core repository, which contains the core Maple functionality. So with this kind of setup, we could then go into other controller software, such as Floodlight, and implement something like a Floodlight Maple adapter and reuse the Maple Core code in an environment like that.
Okay, for our team collaboration, we are using Trello to record all our estimation working time, and we're using GitHub for our codes uploading there. And the total estimation working hours for our group is around like 400 hours, but due to the burn down chart, it doesn't show the whole working load because we started using this burn down chart for March, and for each sprint we actually fulfill the estimation time. And for the group collaboration, we use Slack instead of just the emails to record our collaboration.
So for our project, we generate documentation for the all Maple project, and it's in our GitHub account, and the address is the down of the screen, and you can check it later. So since Maple is an open source project, we really want people to use our project, not just see what we do. So we have this website, sdnmaple.com, which have the overview and the detail about our project. And later, we already built a community which have like 40 people in this industry, which is trying to use our work after we fully finish it.
Okay, so for testing our code, we need to compile both the ODL project with our Maple adapter and also our Maple Core project. So since ODL is a very large project consisting millions of lines of code, it really takes like about 5 to 10 minutes to compile the whole project. And so we need to first compile our Maple Core project if we want to test our code. And after compiling both projects, we start the ODL controller using the graph container, which will deploy our project through this container. And also another important tool we are using to test our code is Mininet. This is a tool which can allow us to simulate a network and also to connect our ODL controller to it. So after we connect our ODL controller to the Mininet, we can ping the hosts in the simulated network, and also we can observe how Maple processes the packets and install the flow rules using some of the commands in Mininet. And at the end of this talk, we are going to give a demonstration of the works we have done. Okay, so for this demonstration, we will go through a tutorial on how to install our environment and actually test it against Mininet. So the first thing we need to do is to download the Git repository from GitHub using this command. And then after downloading the repository, we cd into the directory and cd into the Vagrant directory. We do a Vagrant up to bring up the virtual machine containing our environment. This may take a few minutes, up to 10 minutes, I think. Okay, so we have now set up the Vagrant virtual machine for our environment, and all we need to do is to SSH into this virtual machine and do our demonstration. And as we can see here, we have two repositories representing our project. The first one is our Maple Core, and the other one is the ODL Maple, which contains our adapter for ODL. And we also have the MiniNet installed in this environment. So now we are going to change directory into Maple core to build it. In this Maple core directory, we do maven clean install. This will take about like half to 1 minute to compile this Maple core project. Okay, now we have successfully built our Maple core project. Then we need to change directory to our ODL adapter, which is ODL Maple directory. And then we do a maven clean install in this directory. And because this is compiling the whole ODL project, it may take up to 5 to 10 minutes to compile this whole project. Okay, so we have now successfully built the ODL project, and all we need to do is to start the craft prompt. We do that by run the craft distribution. Using this command. So it takes a while to start this craft prompt and get every features in ODL loaded. And after we see this Open Daylight logo here, we can do feature install ODL-L2 switch -maple. So this will actually install our Maple adapter into the ODL. For now, the craft container is still loading the bundles. After everything is loaded, we should see a print line saying Maple initiated. So now we see the print line of Maple initiated. This indicates that we are ready to go for our testing. So now we are going to open up another terminal and also do Vagrant SSH into the virtual machine so that we can start a MiniNet virtual network. We do so by using this command. This part indicating that we are using a remote controller with the IP address of that. So this is the IP address of our controller being running on our local machine. And then we are going to indicate that for our network, we need a topology of tree with steps 1 and fan out 5. So this will start a network with 1 switch and 5 hosts attached to it. We'll hit enter. And we can see that a lot of print lines going on in the craft prompt, indicating that the controller is actually connected to the virtual network. Right now we can do a ping between 2 hosts. We can do H1 ping H2. Okay, so we can see that the first packet takes 36.4 milliseconds to go through. This indicates that the first package is being sent to the controller, and the follow-up packets are not being sent to controller, and only forwarded to the according to the flow table installed in the switch. The packages are forwarded to the correct host, and we can view the OpenFlow flow table using this command. So we can see here there's 3 rules installed using the Maple. So the first one is it says for a package coming in from port 1 and with destination source MAC address being 1, source MAC address being 1 and destination address broadcast, and we broadcast it to the ports, which was being port 1 to port 5. And the second rule being that the learning switch has actually learned the port information about the hosts, that forwards the packet from host 1 to host 2 directly, and then the same thing happens for a packet going from host 2 to host 1. And then if we do a ping all in Mininet, it pings every host to every other host using this command. And then we also show the flow table for this switch. We can see that there's a lot more rules installed for forwarding the ping packets to each of the hosts.
So in summary, Maple allows algorithmic policies to be compiled to flow rules. Our project implemented a basic version of Maple and wrote an Open Daylight adapter. And we've demonstrated a running example of a learning switch application. Thanks very much for watching.